there are three fundamental concepts in category theory. The first is the definition of a category itself. The second is the definition of a functor. And so functors are things which relate to different categories. The last and final fundamental definition in category theory is that of a natural transformation which relates to different functors. Let me start with an example. So recall that if you have a group G, G op is the group with underlying set G. So it's a group structure on G with order of multiplication reversed. With multiplication defined by, so G1 star G2. So this star denotes the multiplication in G op, and that's equal to G2 G1, where this denotes multiplication in G itself. And you can check that this actually is a well-defined group. It will satisfy identity, associativity, inverse, and so on. Okay, and in fact this op is more than just a way of associating a new group to an old group. It's actually a functor. So it turns out that op is a functor. You can also define it on homomorphisms. Given a group homomorphism F from G to H, we can define F op from G op to H op by just defining F op of G is equal to F of G for all G in G. And you can check that F op is a group homomorphism. I'll leave that as an exercise to you. And so op defines a functor from the category of groups to the category of groups. So this is the category whose objects are groups and arrows are group homomorphisms. Okay. Now there's a theorem in group theory which says that every group is isomorphic to its opposite. And how do you construct this? Define eta G from G to G op by, it's not, you cannot take G goes to G, you have to take eta G of G is equal to G inverse is an isomorphism. We just need to check, eta G is clearly a bijection, we just need to check that it is a group homomorphism. Now it clearly takes the identity to the identity. Let's just check that it preserves multiplication. So eta G of G1 G2, so this is multiplication in the group G. Well, this is going to be G1 G2 inverse, which is G2 inverse G1 inverse, which is eta G G2 eta G G1, which is, this is not quite multiplication in G op, this is still multiplication in G. To make it multiplication in G op, we need to write G1 star eta G G2, we reverse the order. And so you see that eta G of G1 G2 is eta G G1 star eta G G2. So this is a group, is an isomorphism of groups. But there's something very special about this family of isomorphisms. So for each group G, we have an isomorphism eta G. And so this eta G is actually a family of isomorphisms, one for each group. There's something very nice about this family of isomorphisms, and let me explain that in a minute. So suppose you have a group homomorphism. So then you can draw this diagram here. You have G to G op, and you have eta G. You have H to H op, and you have eta H. Now from G to H you have F, and from G op to H op you have F op. And this diagram commutes. In other words, F op circle eta G of G, well, that's equal to F of eta G of G, because F op is just defined as F, but that is F of G inverse. But F of G inverse is F of G inverse because F is a group homomorphism, and so that's eta H of F of G. Therefore, this diagram commutes. And the commutativity of this diagram for every arrow in the category of groups is basically the definition of naturality. So a natural transformation, I'll give you the formal definition in a minute, is a collection of arrows in the target category. So let me give you the formal definition now. So given two functors, F and G, from a category C to a category D, a natural transformation and here the notation is eta goes from F to G, or sometimes we'll write F eta G. So eta is an arrow in some category which we'll come to later, but eta is a natural transformation from F to G, is a collection eta G, eta, let's say A, and this eta A has to be in the category D and should be an arrow from FA to GA. It is a collection of arrows such that one for each object A of C, such that the diagram, maybe I should say such that for every arrow F in the category C between objects A and B, the diagram, so we draw the analog of this, a more general version of this diagram. So we have, firstly we have F of A, and then we have G of A, and here we have the arrow eta A. This is an arrow in the category D. But then we also have, because of F, we have an arrow FF, and this is to F of B, and we have an arrow GF, this is to G of B. This is again, these are arrows in the category D, and then we have eta B. This diagram commutes. i.e. GF circle eta A is equal to eta B circle FF. And in particular, if eta A is an isomorphism for every object A, then we say that eta is a natural isomorphism. So natural isomorphism is a special kind of natural transformation which is made up of isomorphisms. So now just get everything clear. So given two functors f and g, a natural transformation from the functor f to the functor g is a collection of arrows in the target category D, and it goes from f of a to g of a, and this diagram must commute. So the upshot of this definition and the previous example is that eta g, which takes g to g op, okay, but we can think of this g as the identity functor applied to the group G. So you have from the category of groups to the category of groups, you have the identity functor, which takes each group to itself and each arrow to itself. So this is a natural isomorphism between the identity functor from groups to groups to the opposite functor from groups to groups. Both identity group and opposite are functors from group to group. Okay, let's look at some more examples. So recall that we have this functor from vector spaces to the opposite category of vector space, or in other words, a contravariant functor from the category of vector spaces to the category of vector spaces, where for every object v, we define dv to be the linear dual. So this is the category theory language. You can say this is the linear maps from V to K. And now you can also talk about this is a functor given f from V to W. We can define df from dw to dv by df of xi of v equals xi of f of v for every xi belongs to W prime and V belongs to V. Now this functor can be squared, so we can compose D with itself. So we have D squared is a functor from vec k to vec k op. But double opposition is just vec k itself, because if you reverse all the arrows 2 times, you're back to the original arrow. So D squared is a functor from vector spaces over K to vector spaces over K, and it takes each vector space to its double dual. And now we also have identity functor from vector K to vector spaces vec K. And this just takes each vector space to itself. And now I'll define a natural transformation from the identity functor to the double dual functor. So eta is going from the identity functor to D squared. And so what I need to do is, for every object V, I need to define eta subscript V. So eta V. And so this should go from V. So this should go from V to D squared V. So eta V takes a vector V and it gives us a linear functional on dV. So this should, so suppose Z is in dV, then it should give me an element of the field K. and this can be just defined to be z, which is a linear functional on V evaluated at V. So this is for every z in dV and V in V. Okay, so this formula is doesn't really, it's a very nice formula, doesn't really involve what is V and what is Z and so on. It's just a formal kind of nice way to put together things, and because of that it ends up satisfying naturality. So claim is that this collection eta V defines a natural transformation. So what do we need to do? We need to check something. So we need to check a certain diagram commutes. So whenever we have that for every f in vec k from V to W, the diagram we have from V to D squared V, we have eta V, we have W to D squared W, we have D squared F, and we have eta W from W to D squared W. We need to check that this diagram commutes. Okay, so let's do that. So on the one hand we have eta W circle F, and this takes a vector V, and so let's evaluate that. So that needs to be evaluated. So what do you get when you do that? You get a linear functional on dW. So we have to take an element of dW and we have to return an element of the field K. So this is going to be by definition of eta W, this is going to be xi evaluated at Fv. After all, Fv is an element of W. So this linear functional, so here we have for every V in V and xi in dW. So this is xi of Fv. That's the definition of eta W. And that is the same as df of xi evaluated at V. That's from the definition of D. And that is the same as eta V of V evaluated at df of xi. This is from the definition of eta V. And so, but that is the same as so if you look at the definition of D again, this is the same as D squared F evaluated at eta V evaluated at xi. So what we get is that this is just D squared F circle eta V evaluated at xi. So what we get is that D squared F circle eta V is equal to eta W circle F. So that completes the proof of the naturality of eta. Okay, one last example of a natural transformation, which is of a very different nature from the two we have considered so far. Let's consider the categories with one object. So remember that if M and N are monoids, if M is a monoid, there's a category Cm. Let Cm be the category. With one object, star, and Cm, the arrows from star to star in Cm are just given by the elements of the monoid M. And now this monoid M has an identity element, that's going to be the identity arrow, and the composition of arrows will just be given by the multiplication operation of the monoid M. Okay, and so now we can ask what are the functors from a category Cm to a category Cm. So recall, so a functor given two different monoids M and N, a functor let's say f from Cm to Cn, well, there's not much it can do at the level of objects. Must have f of star, this is the star of M, must be equal to the star of N. So let's just give this, it's called the star of N. But then what is more interesting is what it does on the arrows of M. And the function f, so given M in M, so this is Cm star star, which is equal to M. Fm is an element of Cn star star, which is N. So f gives rise to a function which will also denote by f from M to N, and the functoriality of f implies that this function capital F is a homomorphism of monoids, a monoid homomorphism, which means that it preserves the product structure for monoids and takes the identity to the identity. Okay, so these are the functors from Cm to Cn, are just the monoid homomorphisms from M to N. So let me write that schematically. So fun Cm to Cn, this is the collection of all functors Cm to Cn is equal to mon Mn, where mon is arrows in the category of monoids. Which means that this consists of all functions f from M to N, such that f of the identity of M is equal to the identity of N, and f of M1 M2 is fm1 fm2 for all M1 M2 in M. Okay, so that's the category of that's the set of functors from M to N. So now let's ask, given two functors f and g from M to N, what are the natural transformations? So question. What are, so given let's say f and g functors from M to N, the Cm to Cn, what are the natural transformations eta from f to g? So let's see what it means to be a natural transformation. So we must have the following diagram. So we have f of, there's only one object in the category M, so we have f of M, and we have f of star of g of star of M, and we must have an object eta of star of M. We must have an arrow, and this would be an arrow in Cn. So this would be, okay, we'll decipher it later. Let's just write down the definition of natural transformation. So then we have for every M, we have Fm here, and here we have gm g of star of m. This is eta star of m. Okay. So we only have to find there's only one object in the category CM, so we only have to define eta on that object. And so let's just unravel where these things live. So eta star m, where does this live? This belongs to in the category Cn. It's an arrow from f star m to g star m. But f star m and g star m both have to be in n. So in fact they have to be star n and star n. So this is just n. So eta star m is an element of n. So this is in n. And let's say it is let's say it is equal to n. So say eta star m is equal to n. What about f of m and g of m? Well, those are just monoid homomorphisms. So let's rewrite this thing here, sort of unraveling all these definitions. So f of star m is star n, and we have star n, and we have this element n, which completely determines and is determined by eta. And here we have fm, which is also an element of n. We have gm, which is also an element of n. And here again we have star n, and we have n. So the set of natural transformations from f to g consists of the set of n in n such that n multiplied by fm, this is a multiplication in the monoid n, is equal to gm multiplied by n. So this is the collection of all natural transformations from f to g in this setting. And not all these natural transformations are going to be isomorphisms. The natural transformation n is going to be an isomorphism if and only if n is invertible in the monoid n. So yeah, and if you take the special case where m and n are groups, this can be rewritten as so let's just say the natural transformations eta f to g consists of those elements n in the group G, in the group n, such that we can rewrite this rather nicely as G of m is equal to n f of m n inverse for all m in m. I should say here for all m in m, in fact. Okay, so if we use the notation nat, we can call this nat fg, the set of all collection of all natural transformations from f to g.